Happy number. So given a number, let's say 19, what we do is we take both of its digits, 1 and 9, we square them and then we sum them. What we get is 1 plus 81 equal to 82. And we do that again. Square plus 2 square equal to 64 plus 4 equal to 68. And once more, 6 square plus 8 square equal to 36 plus 64, which is 100. And finally what we get is 1 square plus 0 square equal to 1. So any number that becomes 1 when we follow this process is a happy number. Let's take another example of 23, for which we get 2 square plus 3 square equal to 4 plus 9, which is 13. And then we get 1 square plus 3 square, which is 1 plus 9, which becomes 10. And finally 1 square plus 0 square equal to 1. So 23 is also a happy number because it becomes 1 when we follow the same process. Let's take another example of 12, which is not a happy number, and you will see. So we get 1 square plus 2 square equal to 1 plus 4 equal to 5. And we get 5 square equal to 25. We get 2 square plus 5 square equal to 4 plus 25 equal to 29. And you get 85, and then 89, and then you get 145. You keep doing this, and then you keep doing this, and you get 37, and then you get 3 square plus 7 square equal to 9 plus 49 equal to 58. And then we do it again, 5 square plus 8 square equal to 25 plus 64, which becomes 89. So at this point you can continue, but you will realize that 89 is something that you have already seen. So you're pretty much stuck in a loop. If you go back, you will just continue to repeat this entire sequence that you have seen, and this will the loop will continue. So the numbers which do not converge to 1 and which get stuck into a loop are non-happy numbers. So 12 is not a happy number. So the problem that we have is, given a number, we have to find out whether it's a happy number or not. So we have a function like is happy, and then we have a number n. We have to write an algorithm to determine whether this n is happy or not. So we are done with the understanding the problem. Let's look at the approach for solving this problem. And just with observation, you will see that determining a happy number when it is actually a happy number is pretty easy. We just keep taking the sum of the squares of its digits repeatedly and keep doing the same until it becomes 1. Similarly here, we keep doing the same and then we reach 1, and then we say that, okay, this is a happy number. The problem occurs when we are dealing with a non-happy number, in which case we will be stuck in a loop and we won't know at any point whether we are stuck in a loop. So look at 58, we don't know whether we are in a loop. At 89, we have no way to know whether we are in a loop unless we have access to the previous history of numbers that we came across. So when we are 89, we somehow need to look up this entire history to see whether 89 was seen previously, and if yes, then we are in a loop. And how do we store the history like that? So the best data structure for solving history like that, which allows order 1 access, constant time access, is of course a hash set. So we use a hash set for solving this problem. What we do is, every time we encounter a number, we check whether that is in the hash set or not. So first of all, we will see 12, and then we will have 5, and then 29. At every point, we will see that, oh, the new number does not already exist in the hash set, so we will add it to hash set, and then we'll keep doing that, 85, and then 89, and then 145, and keep doing that. We will reach 58, and then 89 again. And when we reach 89 over here, we will check in the hash set that okay whether 89 already is there in the hash set or not. And if it is there, which is there, we know that this is not a happy number because we are in a loop. So we return false from there, which saying that 12 is not a happy number because when we were doing this process here, we got stuck in this loop, which we detected with the help of hash set. So let's take a look at the complexity of this solution. Let's say the length of the loop is L. So this is the length of the loop. And let's say the length of the other steps that we took is C. So the total time complexity will be order of C plus L, because that is the number of steps that we are going through in determining whether this number is happy or not. And similarly, this is the worst case complexity. Similarly, we have the space complexity where we are storing all the history of all the numbers starting from the first number. So that is also order of C plus L, which is great. But we need to think whether if there's a way to optimize the space complexity, if we can do something without using a hash set, or is there a way to detect this loop? And that is our approach number 2. So if you look closely, you will realize that this problem is similar to a problem in linked list of loop detection. So if we have a linked list like this, and we have a loop over here, what we do is a code for this particular problem. So we have this function here is happy, which is supposed to return whether a number is happy or not, in a which is supposed to return a boolean. So what we do is we initialize, as we discussed, we initialize two different pointers, slow and fast, and we also define a number called a method called happy, which is able to take a number like this and it's able to compute the. So before we go, I also want to mention that there's another approach for solving this problem, which is able to solve this in order of 1 and a space complexity of order of 1. Which a very common approach for finding a loop in a linked list is using a fast pointer. So what we do is we take two different pointers, and with one pointer is moving by a distance of 1 every time, like this is called a slow pointer, and this is the fast pointer moves by a distance of 2. So from here it will go here, and this slow pointer is here. Now the fast pointer will go here in the next step, and the slow pointer is here, and then the slow pointer will move by 1 and the fast pointer will move by 2 and reach here, and then slow pointer will reach here, and then the fast pointer will again reach here, and over here they meet. And that's where we say that if slow pointer is able to meet the fast pointer, we will say that there's a loop in the linked list. And the same is the approach we can apply in this particular problem, where we take two pointers, we keep moving like the way we move in here, and eventually if our two pointers reach at a particular location, then we say that this is not a happy number. And in the cases of happy numbers, for example this, our fast pointer will eventually reach 1. So if the fast pointer reaches here or the fast pointer reaches here, the next step from this would be, if it is here, then we know it is 1, then we return that it is a happy number. If it reaches here, then if it takes 2 steps, then 1 square equal to again 1. So from here it will directly go here, and then we always will reach 1. So this way, using slow and fast pointer, we are easily able to detect the loop in linked list as well as for the happy number problem as well. And the complexity for this algorithm will be the same. It will be order of L plus C for the time complexity. But for the space complexity, you see that we are not using hash set anymore. So the space complexity would be a constant complexity, which is order of 1. Which generally the interviewer would not expect from you. But if you are still curious about it, you can search for an article on Wikipedia for digital root. and over there you will be able to find the formula for computing the digital root for a given number, which will tell you whether it's a happy number or not. So check it out if you're curious. Otherwise, the interviewer does not expect this solution from you, and this is good enough. So thank you for watching, and that's it for this video.